Okay. Thank you very much for inviting or accepting this talk. I would like to. Okay. So I would like to talk about practical problem in seismography, and okay. So in the context of geophysics, there is a very computational intensive problem that when geophysicists would like to figure out what's below the surface, then they use explosions or mechanical excitations to send waves into the in subsurface, and these waves reflect back from the various layers of this sedimentary picture, and these waves scatter back, and they are detected by receivers, which measure how the the surface is oscillating, and they collect this data, and from this data that they collect here, they have to reproduce the structure below. So this is an inverse problem. So you have to figure out from the returning waves what is below the surface, and to do this, they have to solve the wave equation basically in this geographical context, and the problem is that they have to calculate all the waves starting from the source develop, and how the waves, and they also do a calculation backward from the receivers. They send the signal numerically back, and they have to calculate the correlation of these two waves, which was going down and going up. And out of this, they can generate a picture of the likely structure of this layer. Of course, there is then a second step. First, they try out a trial layer structure. They compute using that, and then using this data, they get an improved geometry, what is below. And then based on this improvement, they change the expected field down there. The field means they have a model what are the sound velocities below, and they then refresh the sound velocity picture down here, and they again simulate the waves and the backscattered waves, and do this many times. And just to characterize this, they like to use 1,000 by 1,000 by 1,000 grid. That means 1 billion points, and that's a demanding problem. It takes sometimes days just to calculate one such situation on supercomputers or specialized machines. So as it's here, we need thousands of these simulations, and then so it's demanding for classical computers, and there is a cost associated with these computations in large data centers. And what we tried is to do these calculations with novel methods, basically quantum computing. Here I will outline how this could be solved using quantum computers. But then today's quantum computers are not capable of carrying out this calculation at all. And therefore, we turn to tensor train matrix product state methods to solve this problem. And then I will show you a toy problem, which used in geophysics, a 2D model where the physics is very simple. There is only one sound velocity, and in the real geophysical context, there are several velocities like transversal velocities, longitudinal velocities, and even more. And there is a more complicated wave equation than what I will show you here. But this can be, of course, added to this model gradually. And so this is a toy problem, but normally in the geophysics literature, this is the model where they try first the new computational methods because it can be done on a laptop. Okay, so okay, the seismic forward modeling is okay. The first step for this full waveform inversion. The full waveform inversion is basically when you reproduce the layer structure, and then quantum mechanically, you hope that instead of 2 to the n states, you can use n qubits. In this case, if you take 1024 grid points to the third power, that means you need roughly 30 qubits to represent this, plus a few for computational reasons. So if we would have an error-corrected quantum machine, this problem could be a good one because you need just 30, 40, something like that qubits to do this. And instead of that, we will today do here the matrix product state simulation for the same problem. And the physics is this. So you have a wave equation in 2 dimensions, because this will be a 2-dimensional problem. We will have 256 by 256 grid. So it will fit in a laptop, basically. And then you have this wave field. X is the horizontal, Z is the vertical axis. You have a Laplacian, and you have this is the square of the velocity in point X and Z. And naturally, you can solve this by discretizing the problem. This is the discretized Laplacian. This is the discretized velocity field. Lambda is the time step divided by the length of the grid physical length. And you have to make sure that you choose delta t and h such a way that this scheme is numerically stable. Okay. So in a quantum representation, we go through very quickly. You basically code the coordinates. So you have, in this case, 256 grid points horizontally, and then that is 2 to the 8, and you need 8 binary variables to code all of them. So this is basically, you have the coordinate x from 1 to 256, and this is just the base 2 representation of that number. So it's very, very simple and similar for the vertical. And then quantum mechanically, you have a velocity operator, which is just a diagonal operator in this abstract field of binary numbers. And whenever that will be possible, you can use a quantum read-only memory to store that, or you can express it as a function operator. Okay, and to carry out the Laplacian, you have to sum for the neighboring points. So like if you are on a grid in ij point, which is x and v, you need the left next, right next, upper, down, and you have to calculate this quantum mechanically. You have to implement this on this binary sequence, which is modulo 2 to the n operation. And then there is a established theory how to do this. And you do a bit level transformation and you create a forward and a backward shift operator, which shifts x with 1. So you add you go from grid point to the next, and that is a complicated binary operation how you carry this computation in base 2. Okay, and basically there is a nice quantum mechanical implementation in terms of Toffoli gates, which I think everybody heard about, that it doesn't exist still in reality. You have to create it from C-node gates, so that's a complicated issue. But then you create basically this quantum mechanical operator which acts on these bits. You have to organize the bits so that there is a more significant bit. If you shift that, then you go to the other side of the problem. And the least significant bit is just when you go to the next. Okay. So you can carry out this. I skip basically, and I turn to the tensor train representation. In the tensor train representation or matrix product state, you have this usual decomposition of the wave function, and you have a bond dimension for these matrices, which is chi, and you have chi by chi by 2 matrices here, and you compress, you have to compress the wave field, you have to compress the velocity field, you have to implement the matrix product state operation of this addition, etc. And then you get matrix product operators which carry out the same Laplacian. Then you have to multiply with the compressed velocity field, which can be complicated, but hopefully not infinitely complicated. And then when you carry out this operation, you have to do the usual stuff, but everything within the tensor train calculus, so you never sort of recreate the field. But in this demonstration, I will recreate the field. Okay, I skipped the, we can look at later the concrete Python code. And then I show you a simulation where we did this with, we did a direct simulation. So it's just this step-by-step simulation and the matrix product state simulation. We set roughly 128 bond dimension, which is very large. It's larger than actually the current calculation, but you hope that when you scale this up at about 10 to the 6, so at 1 million points, you will gain in speed. So this is how it looks. This is the velocity model. The colors code the velocity, and this is your wave. And the upper one is the truth, I mean the discrete Laplacian simulation. And downstairs, you can see the matrix product simulation, and they are quite nice. So this is just a proof that this is possible. And I have to say that the geophysics community didn't get that far with this method. Okay, and I show you the temporal simulation. This takes much more time on your laptop. This runs in seconds or minutes, more like seconds, and this one like 10 minutes or something. But you can see that it's pretty much able to reproduce this quite complicated field. So this is how the wave explodes from the middle. And then I just summarized that this is the discretized version. The quantum version would operate on quantum computer with the gates I showed you. And then this is the matrix product state simulation basics. So we have several problems, of course, which have to be solved until this scales up. So it depends heavily on how much you can compress the velocity field, whether there are enough regularities in it. We hope that there are, because the layers are not just random noise. And of course, you can generalize this to any dimension, to 3D dimension. And of course, another thing is to run it on GPUs or TPUs, etc. Thank you very much.
Thank you very much. Gábor, time for questions. Oh, Tony.
Thank you for a very nice talk. How robust is this method? I mean, you use the simplest wave equation to solve. If there are nonlinearities, for example, or other issues, so how?
So my collaborator is just retired from Chevron, where he did this in his entire life, and we are working together. And the problem set is coming from him, not from me, of course. And yeah, we know the exact equations, like it's stress tensors, and it's not just a Laplacian. There are other terms, but this would just add to the complexity of that vector, and then of course the scheme will be also bigger. But these are not the exponential problems. That's the hope, that that you have to do this like nine times more complex way in reality, because the sigma tensors have 4 indices, etc. But that a cost which exists also in the direct simulation. So we hope that it will be faster from 10 to the 6 grid points upward. That's
okay, further points? Ah.
Thank you very much. Very nice pedagogical lecture. Actually, the density field, or whatever you are calculating, and how the complexity of that determines the speed up. I mean, does this work for any complex distribution of densities or whatever or if there are some sparsity in that there are large blobs or whatever that may make it even faster or even more compressible by this method?
Everything depends on the complexity of the velocity field. and how much you can compress it using the tensor train or matrix product state. And you have to see how this bond dimension scales with the scale of the problem. And then we hope that this small part is the most complicated part of actually of that picture. So we try on that, and hopefully the bond dimension will not go to infinitely high. And if you would do this for random velocity field, then you would gain nothing. If you would do it for a homogeneous field, then it can be solved exactly, and we are in between. That's the.
Okay, I would have also a question. It was very interesting for me actually, but the question is, since we are on the GPU days, so the original classical problem shouldn't be solved very easily with ray tracing, which is really the exact case that you with ray tracing technique.
Ray tracing is one of the methods. It's a long wavelength approximation, and the industry knows that, but it's not sufficiently good for this problem, because in the quantum case you have entanglement, so it's a very entangled problem in this representation, and they do it on GPUs, of course. That's why we try to do this.